Hi, I'm Andrea. I'm a PhD student at the University of Maryland, and I'm going to be talking about a Chi 2020 paper, Sense and Sensibility, Evaluating Information Olfactation, that I co-authored with Biswaksen, Patnaik, Akazue, and Niklas Elmqvist. Information olfactation is the idea that we can use smell to represent abstract information. Why would we want to do that? Well, we can use smell to transmit information without requiring the user's visual attention, if they need to be looking somewhere else, like while they're driving, for example. And this also applies to situations where the user can't see. Another application is in instances of slow-moving data or gradual processes, things that change slowly in real time but represent an overarching pattern that's relevant to a work process, like the hourly changes in a stock market set of indicators. So to start off, we should be clear on what, in general, information olfactation is. So it's the design space and implementation of displays that use smell to convey abstract information. That's information without a natural spatial mapping, like the price of a particular stock, students' grades in a class, or the major that that student is enrolled in. So in a study like ours, where we're evaluating information olfactation, we want to know not only if we can exploit the human olfactory system to convey features of data, we want to know how well we can do it and using what techniques. So I should belabor the point here before we move on that we're talking specifically about abstract information. We're not talking about, say, adding the smell of baking bread to a VR scene that's set in a bakery to enhance immersion. We're talking about representing data through smells in a way that supports data analysis. For example, making an increase in the Dow smell like mint, while a downturn smells like a lemon. And we introduced the concept of information olfactation in our 2019 TVCG theoretical paper, and our main contributions there were in our task taxonomy, in our definition of a design space for olfactation, and in the prototype BizScent 1.0 that we built for the study. So I should give a little bit more detail on this as the background of our current work to demonstrate how this fits in together. Starting with our task taxonomy. So there were 5 broad task types in our taxonomy, and for each one of these I'm going to give a sort of natural mapping example just to illustrate what I mean. So information recall is sort of like when a smell brings you back to a childhood memory, for example. A smell can assist with information recall by having these associative memory bindings. Object localization and tracking is, for example, a bloodhound helping the hunter to track a fox. Feature detection and discrimination, for example, picking out nuances in the bouquet of your favorite wine. Temporal reasoning could be when you smell something new in your surroundings. And associative reasoning, which tends to be cross-modal. So it's been indicated that the scent of lemon, for example, makes people think of sharp and angular shapes. And that's what I mean by cross-modal here. So for our study, we decided to focus on feature detection and discrimination. And as a part of our design space, we introduced these 3 olfactory mark types. We have simple smell glyphs and the fragrance classes into which they fall. We have molecular bouquet or complex glyphs that cross classes. And we have airburst, which is sort of a pseudo mark that's part mark, part substrate or medium of conveyance. And because scent is so heavily cross-modal, the perception of smells depends not just on the chemical composition of the air, but also its aspects of the medium that it's conveyed to you on. Now, for the study that we conducted, we decided that it would be most appropriate to limit ourselves to evaluating the performance of discrimination tasks using only modifications of the simple glyphs and the airburst, so we drop our molecular bouquet. And when I say modifying it, I mean we use these different olfactory channels to change the way, change the smells that people are experiencing. So we have these 5 channels: direction, scent intensity, air flow rate, the qualities of the air like temperature or humidity, and the pattern of the mark or the smell that the user is exposed to. which is sort of like a meta channel, and then it allows us to vary the composition of the smells that the user is experiencing. So evaluating these channels was the primary focus of this study. So let's talk a little bit more specifically about our study design, which I should point out was pre-registered on OSF, which is a best practice for open and transparent methodology. And you can check out our pre-registered plan by going to the page on the screen here. So as I said, evaluating our olfactory channels was the primary focus of this study. We decided that we would be using a desktop display for our user session since it was the most practical and the least invasive approach. But the technical requirements of implementing this without a head-mounted display were onerous enough that we restricted our evaluation to our other 4 channels only. So we have our scent intensity, the airflow rate of the airburst, pattern, and specifically the scent type that's used, and qualities of the air. So specifically, we focused on temperature. And these 4 channels represent elements of our first experimental factor here. So we have one experimental factor. You probably guessed that we also have a second factor here that is the type of information that the user is trying to make sense of. So each task used an olfactory channel to represent data that was either quantitative or ordinal or nominal. And in other words, the user had 4 channels and 3 different types of data that they needed to explore all combinations of. And we wanted to repeat each trial that the user experienced several times to account for individual variations. So we have 36 trials per participant to answer our research question, which is namely how effective these channels are at conveying these types of information to the user. So who are our participants and what did we actually ask them to do and how did we support them in doing it? Well, we had 20 paid student participants aged 22 to 30 years old, and 12 of them identified as men, 8 as women. And we should talk about the apparatus. This is our how did we support them. And now in our theory paper, we introduced a prototype called Biswaksen 1.0. Of course, we just called it Biswaksen at the time, but we have since developed a brand new prototype, Biswaksen 2.0, for the purpose of this study. This is an olfactory display system that was designed specifically to evaluate our research questions. So Biswaksen 2.0 uses 24 different fragrance pods to vary the scent type and the intensity. It uses 3 airflow fans with variable speeds. It uses a Peltier module and a heating coil for temperature control. We used ultrasonic diffusers to vaporize the solutions of aromatic oil and water with varying fragrance and oil concentrations. This system was controlled by a tower that we built using an Arduino Mega microcontroller that we flashed with our C++ sketch and an application that we wrote in C# and Unity. The control tower walked the user through the experiment, first presenting them with a tutorial and then asking them 3 questions per experimental factor combination. Once participants were introduced to the study, they began the sessions with blocks of experimental factor combinations, so a combination of one olfactory channel and one data type that were randomly selected by Biswaksen 2.0. The system then played them a tutorial demonstration and afterward asked the user questions about randomly selected observations in a synthetic data set. The participants were run through 3 repetitions where they had to answer a question about the data. And after they submitted their answer, they gave a Likert value response for how certain they were about their answer. After 3 repetitions, the system either randomly selected another block of an experimental factor combination, channel and type, or if there were no combinations left, the participants exited the experiment. Users were asked questions like the one shown here, and they could respond to quantitative questions by moving the continuous slider, ordinal questions by moving a slider that snapped to the nearest value, and nominal questions by clicking on the button. The data that we used to evaluate task performance were Likert scale, self-reported confidence scores after each trial, a Boolean measure of whether the answer was correct or not, the magnitude of the error, where that was applicable. And these errors were normalized around a mean of 0, and also the amount of time that it took the users to respond to each question. We had 3 main predictions about how our experiment would turn out. First, we expected that users would have a better correctness when interpreting nominal data using the scent type channel relative to their use of other channels. And second, we expected that participants would have lower errors interpreting ordinal and quantitative data using scent intensity than they would using other channels. And finally, we expected that participants would have higher errors interpreting ordinal and quantitative data using the scent class channel or the scent type than they would using other channels. So let's talk about our results. If we look at the effects of different data types as a factor for user task completion, the error size and the correctness differences are negligible. There's also very little difference in the Likert scale responses to confidence. And the participants did take slightly longer to answer questions about ordinal data, but overall, there's very little difference across these different data types when taken in aggregate. Now, the results that we were most interested in were the effects of our different channels on the normalized error, on the correctness, and on the completion time or response speed for the questions the users answered about the data. We found that the error was higher for scent intensity in both ordinal and quantitative data, significantly so for the ordinal data. For quantitative data, we found that temperature had the best, that is to say the lowest error size, and it had a fairly tight distribution around the mean. Scent type had a higher error for quantitative data than the airflow rate or the temperature. Within our correctness measure, we found that scent type performed significantly better than the other channels for ordinal data, while scent intensity had a lower, that's to say worse, correctness than the other channels for ordinal data. Finally, we found that participants responded fastest to our questions based on changes in the airflow rate for all of the data types, while modifying temperature resulted in slightly longer completion times. And once again, that is for all of the data types. So in terms of confidence, the users felt generally more confident for the channels that had direct effect on the medium of conveyance, that is to say the air burst, than they did on the channels that directly affected the scent in the air, the scent type or the scent intensity. But most of the trials, the users felt a fairly high level of confidence about their answers. We also asked them about their experience. Participants found that our display was fun to use, and they thought that it was easy to adjust to using olfactory channels to interpret data once they got the hang of it, but there was a bit of a learning curve, and they felt that it wasn't very efficient. And that speaks to our notion of olfactation being a good medium for representing slow data. That's data that represents overarching themes or gradual processes. So we prefaced our results by mentioning a few predictions, and there were 2 main surprises for us in our results. First, the scent intensity did worse than we expected. We thought that scent intensity would be the best channel for interpreting quantitative data, but it turned out to be the worst channel for all data types. Second, we were surprised at how well scent type, or that is to say the pattern channel, performed. And we thought that it would be the worst channel for ordinal and quantitative data, but it wasn't. In fact, it was the best channel for ordinal data. And we predicted that it would be the best for nominal data, and that prediction did wind up being true. So to recap, we evaluated our theory of information olfactation. We built a really cool looking olfactory display system to do it. And independent of our olfactory channels, we saw very little difference between the user error, the correctness, or the completion time by data type alone. But when we evaluated our channels as factors, we saw that temperature outperformed the other channels for quantitative data, while scent type beat the other channels for ordinal data and nominal data. And that is our study. Thank you for watching. You can check out a preprint of the full paper at the link on the bottom of the screen, along with anonymized user data and all of our pre-registration materials.